Thank you for staying so late. I'm Xintong Yang. I'm from Cardiff University. So I'm going to present a work that I've done for my last PhD project 2 years ago for general affordance-based manipulation. More specifically for contact-rich object manipulation. We took examples to do this entangling tasks. This is a paper that was published on neurocomputing last year. So basically, I'm from a group led by Dr. Zhe. So we did manipulation as well. We did learning-based SLAM manipulation, and I was interested in reinforcement learning-based manipulation, basically. And at the moment, I'm also doing deformable object manipulation using physics-informed approach as well. So just quickly, the contact-rich manipulation tasks that we were interested in is the tasks that involve more fine-grained and effective control. So delicate context information that the robots need to be more concerned about, and they are difficult to use handcrafted small skills like lifting or small primitives that we can use for pick and place tasks. And in most of the cases we like to avoid damage or large movement to the surrounding environment. And more importantly, for most of these contact-rich tasks, the location where the gripper grabs on the object is important for the downstream manipulation task to be successful. So it's got a sense of aspects of task-oriented grasp estimation in there. Right. So we investigated a example task to just to disentangle this sort of hooks in a simulation. So this can happen in many cases in the household industry where things can be entangled together. So what we did is that we took a two-stage approach using a off-the-shelf deep learning-based pose estimation network, things like GraspNet. So they are very mature in terms of predicting where you can grasp the object firmly, stably. And then from that grasp poses, we start with a reinforcement learning approach to try to manipulate the object so that the grasped object can be separated from the entangled pile of things. So we did 3 examinations. So first of all, it's like a simple handcrafted straight lifting up motions started from the task agnostic grasps. And then the second thing is that we use reinforcement learning, but then there was actions-based design by one of the previous paper, where it's 25 the location where the robot gripper can move to after the grasp happens. And then we did another baseline with the reinforcement learning with just say 60 condition-space nudges around the end effector tip. And then so the task agnostic grasp were coming from this GraspNet approach. So basically give it a point cloud of the scene, and then it predicts a bunch of grasping poses that are supposed to be stable for the robot's grasp. But in reality, most of them are not really approachable. But anyway, we managed to filter those and get those grasping poses that actually can be reached by the robot. And then we start the manipulation from there. And then we designed a reinforcement learning rewards for the manipulation policy to actually separate the grasp hook, and then to try to not drop the hook during the manipulation, and then try to not move the object out of the workspace, and to minimize the overall movements that was caused of the other objects during the manipulation. So, and then we just did some training on a simulation in Mojuco with a few different kind of shapes, hook and numbers. Just start with a configuration that they are tangled together. And what turns out is that with all these motions, or like even the straight lifting up motions, there are certain percentage of successful manipulation that can be achieved. But the problem is that even with reinforcement learning, there's still a large portion of unsuccessful manipulations, and there are always certain object droppings during the manipulation, and there are always some sort of surrounding object movements that sort of unavoidable. So we start to we started to think, okay, that could be the grasping, the choices of different grasp poses. So just shows a little bit of demo of how it looks like. So this is some of the failure. Straight lifted thumb motion, you just lift it up. So rare success, but you need to first just sort of recognize which location to grab so that the robot can separate it. So this kind of actions in the previous work, it sort of causes too much movement to the surrounding object, and it makes the contacts among the object and the gripper more drastic, and it's easier to fall. But nonetheless, there are some success cases that can achieve. And for the 60 Cartesian nudges, you also got some failed cases and successful cases, which means that reinforced learning with the right grasp poses, reinforced learning can sort of separate them with a good small movements of the effector. So, and then what came across is this concept of affordance from the psychology field, and basically we're saying it's about the knowledge of what can be done with the object by an agent in a certain environment state. And in robotics, we use this mainly just to use it as whether an action of the robot is executable in a certain state and what are the consequences of executing the actions. So we actually published a review paper on this topic, how this concept been used in recent years. And what came across was this two paper with a quite elegant definition based on the reinforced learning, the Markov decision process framework about affordance. So with a concept called intent, which is basically the desired next state where the robot, or where we like the user like the robot to achieve at the current state, given a current state and action, and the affordance is defined in the Markov in NDPs as the relations in which we get a set of state actions that can sort of achieve the desired next states that we want the robots to achieve. And then we thought, right, this is more about in terms of the prediction of the dynamics related to its affordance. So we thought it would be more useful we can predict arbitrary consequences of the actions rather than just the dynamics aspect. So we sort of generalized it a bit to include this concept of general intents that we actually want the robots to look at any sort of user-defined measurements related to tasks given a state and action, and then the affordance is then defined by a set of a relation where a set of state and action that can actually achieve the desired desired measurements that the user or the task is relevant to the tasks. So an actual implementation looks like this. We basically, for this hook, this entangling task, we define three measurements, which is basically whether the gross object can be separated, and how likely the object will be dropped, and the average movement of the non-gross objects. So given a current state and the gross spin pose, right? And then the affordance prediction model will try to predict the three estimated values given a gross spin pose, a state, and the policy, right? So basically, it's trying to predict how this robot can perform, and how good it can achieve given the current state and the gross spin pose. And based on that, based on those predicted performance, so we get a point cloud scene, we get all these task agnostic gross spin poses given predicted by the off-shell model, and we kind of predict these three matrix of different gross spin poses, and then we can come up with filtering strategy to filter these gross spin poses before we actually get the robots to start manipulating, right? So we basically come up with a few filtering strategies, and saying that if this gross spin pose is the predicted success rate is below some threshold, we don't want it. it's above some kind of threshold, we want it. Or if it's more likely to drop an object, how likely is it? We don't want it. Or if it's causing too much movement, based on the prediction, we don't want it. So, and it turns out that by filtering those grasping poses with this filtering strategy, we get a significant improvement on the manipulation performances. So basically, this color one are the performances that are using affordance prediction and the filtering strategy. So, and what we also found is that, so that leads to the conclusion that a great portion of most of these tasks, grasping poses, are actually not always useful for the given specific contact-rich manipulation. So it's reasonable as you can think you don't want a robot to give you a cup of hot water by grasping handle and then hand it to you, right? So most of the you need to be, we want the robots to be careful in terms of how it selects the grasping poses for the sake of the downstream manipulation tasks. So for this specific task-wise, this entangling, or actually mostly contact-rich tasks, are very dependent on the grasping poses that was selected by the robots, and trying to avoid poses that easily drop object, poses that maybe can cause more contacts with other object that actually already can increase the success rate, because we got this. I think the second and the third strategy is trying to select the grasping poses with less object dropping rate and less movements, predicted movements to surrounding objects. And so very briefly, we propose this general affordance theory, which leads to the implementation of a general affordance-based manipulation framework. And actually, with these specific tasks we investigated, it can improve the manipulation performance by just filtering the task agnostic grasping poses based on the predicted performances. And in our future, there's actually a lot to be done. So I think while I was doing this, later on I thought there's a strong connection between the affordance that we're talking about and the value function and the reinforcement learning. So because if you define the reward function in terms of certain user measurements, then the prediction of the value function is actually quite similar to the thing that I was predicting in this, just for the sake of the filtering strategy. And then there are other ways to use this kind of general affordance theory. You can use it to guide your exploration. You can use it to sort of limit action solution space, things like that. And then one big limitation is that it was only implemented in the simulation, mainly because the perception challenge for this kind of contact-rich task was just too difficult. And yeah, so thank you. And you can scan the QR code. This is our paper and some research information. Thanks for your attention.
Right, time for one question while Jack is coming up for the next talk. Any question? One question, we have time. No? All right, okay, let's thank the speaker again.
I think you need help to plug in.